I'd like to thank the organisers for the invitation. It's great to come to Germany and give a talk. I had a bit of a stroll in the woods around here yesterday because I went downtown because I had to get something to eat, so there was some motivation. Here's a picture of our lab. We have a dilution fridge there with a magnet. We have a second one now. This is a bit of an old picture. And we're going to get a third. And I'm going to talk about some of our experiments at low temperatures with our cavities and coupling to spins and looking at some low temperature physics. Here's a brief photograph of the group, a few postdoctoral staff and students. I've been working on microwave cavities for a long time for various applications. Here's some of the types of cavities we've looked at over the years. Whispering gallery cavities at microwaves since the early 90s. These reentrant cavities, which are basically 3D lumped cavities, where there's a post inside a cylindrical cavity. It doesn't have to be cylindrical. It forms a capacitance and an inductance, and you can make a 3D lumped circuit resonator. And more recently, we've looked at making arrays of these. I'm not going to really talk about that today, but that's some interesting physics you can do there with topological systems and the like. And then normal TE and TM cavities where you might put a sample of spins in the middle where you've got all your RF field. So what I'm going to talk about coupling to magnons is that we have used 3D lumped element cavities, you could call them, or reentrant cavities. And what we did, I guess, to enable this high coupling to spins is that we invented this multiple post structure where if you put two posts inside a cavity, you would have two modes, and depending where this capacitance, which is the gap here, is in phase or out of phase, you can do what we call a bright or a dark mode with a sample in the center. So this is the RF field, and if you can see if these are in phase, these two posts mimic a single post, and most of the field will be outside like it is for a single post. And you can see here there's some mode shape, and if you put a sample in the middle, you'll get very weak coupling. So we call that the dark mode, and we generally indicate that with two arrows up to show that these two posts are in phase. And then this bright mode where they're out of phase, the RF field is focused into a very small volume. So that's very unusual for a normal cavity. It's very hard to focus magnetic field. And so that's what was the strong point of this when you want to couple spins with photons. So this is some old work where the first experiment we did was put YIG sphere inside these two posts. Publication was delayed a little bit because our university decided to write a patent, but eventually came out in 2014, and we got extremely strong couplings. And this shows those results where we got about 2 gigahertz normal mode splitting when we created our cavity Magnon polariton. And you can see the splitting there. And this is the basic experiment. It's your standard low temperature experiment where you put attenuation on the input lines and amplifier on the output lines. And the nice thing about this experiment, about this really large coupling, is you can actually see your Kissel mode over a broad frequency range. Okay, so we had a nice first talk about using these as a transducer, and we've got the goal to use this as a transducer to look for dark matter, because in our lab we also do fundamental physics experiments, and there is some form of dark matter that's meant to couple to spins, so we're formulating to search in this regime. So we also showed that you could make multiple post structures and make effectively engineer the types of modes you wanted to interact with your spins. So here we created this situation which was dubbed super strong a while back, and we could get a whole lot of different modes in the really strong coupling regime. We could also sort of simulate a whispering gallery mode doublet coupling with time reversal symmetry breaking. We saw this effect with paramagnetic Fe3+ spins in Sapphire a while ago, but we could mimic this time reversal symmetry breaking as well. Okay, now on to new stuff. We had the idea to look at lithium ferrite and see how it couples in one of these cavities. So we did that, and we made this. We used one of our old cavities. We could have made. We had quite a small sphere, 0.46 millimeters, and we could have re-engineered this cavity to get stronger coupling, but it wasn't our main goal to just get a large coupling. The good thing about lithium ferrite is that it has twice the spins per unit volume compared to YIG, so you can get stronger couplings for the same size sphere. So if we had the same size YIG sphere, we'd get a much smaller coupling. Anyway, so we measured this cavity, and we noticed, we made two cavities actually, I should emphasize that. There's a high frequency cavity and a low frequency cavity, so these results show two different cavities, and the main difference is the gap spacing of the effective capacitance in the 3D LCR circuit. So here's our high frequency cavity. We call it high frequency because the bright mode was at 9.5 gigahertz and the dark mode was lower, which it doesn't couple as strongly, so we can't see it as well. And in our low frequency cavity, we got the frequencies lower. And the interesting thing that we saw in this first experiment is we got our typically strong coupling regime. And in the low frequency results, we saw this, the Magnon actually had a zero field value and didn't start from zero, and it turned over. It turns out that was due to anisotropy and saturation. It's explained in the paper. I'm not going to really explain it here. So we thought we would push down the cavity frequencies to get more closer to this regime. And in this one, this mode actually intersected this twice. Here there was quite a bit of loss, so we didn't really hit the strong coupling regime because of the loss, but here there was strong coupling. And this is the dark mode. So if we could engineer the bright mode down here, it'd be much stronger coupling. This is just sort of a small coupling in comparison. What are those values? The values are here. The types of couplings we got in this experiment were for the bright mode, 250 megahertz, 240 megahertz. And when we tuned the low frequency cavity closer to that point, we got a higher coupling on the order of 68 megahertz, even though it was the dark mode. Okay. So so this is called, this effective turnover point is called as mode softening, and combining with the normal Zeeman effect, you get this turnover. And so then we investigated what happens as we push just through a normal two-mode model. If we push the cavity frequency closer to this value, and what you get is this enhanced area of coupling when you change the magnetic field. This flattens out the frequency, flattens out with magnetic field, this regime here, the coupling. So where if you tune away from that, then it does not. And what you find is that at this point, if you tune the cavity to be exactly at this turning point, you get rid of the second derivative sensitivity to magnetic field fluctuations. And that what causes this to be sort of a broad coupling regime. So that was an interesting effect. The line width of the mode isn't as great as it is when it's far away from this point, but it was still pretty good. Okay, that's the latest we've done on the Magnon scene. When I'm talking about spins, I want to also look at what we've been doing with silicon. As we saw in the previous talk, we had a bit about silicon. We published this last year, and what we did is we got some isotopically pure silicon and we made whisper and gallery mode resonators out of them. So first we got this long rod of isotopically pure silicon. We didn't want to damage it or do anything to it, so we decided just to make a resonator out of it and excite modes in it. And if we approximated the shape of this, because you can see it's not a clear cylinder, we could calculate the modes in there and roughly know what they were, even though we couldn't really simulate all these bumps on the side. It was almost a cylinder. And we could excite multiple modes. So what we've done a lot of work in the past is using crystals, using them as the resonators themselves and looking at the interactions of the spins in them. So let me just take a side step before I keep talking about silicon and just say a few slides on this technique. It's a multi-mode or whispering gallery mode electron spin resonance technique where we put a large crystal of centimetre size in our dilution fridge and we look at multiple modes to do spectroscopy as we change the magnetic field. So we've published a few papers looking in sapphire crystals. We saw this time reversal symmetry breaking with Fe3 plus ions. We've looked at YSO. We've looked at YAP. And we've looked at its low temperature properties. So we thought we'd do the same here. Now in this long rod there's a lot of modes, and how do you support it in the cavity without degrading the Q and without just having too many modes that you're not sure what you're doing. So first we just loaded it in the cavity like this with Teflon spacers, and this is a lot of the measured modes. We had a natural silicon, which wasn't the best sample. You can get better Qs in natural silicon. There's no reason why the electrical Q should be different to the isotopically pure silicon. Nevertheless, we could see that the cavity was degrading the Q of some of these modes. So we built in these Bragg reflectors at the end, which takes away the conductive losses at the end here. And when we did that, a lot of these modes became higher in Q factor, and there's sort of this periodical structure where the Bragg reflectors become resonant and anti-resonant. But nevertheless, we could get Qs, electrical Qs in this sample of the order of 2 million, which was, I looked in the literature, the best I'd seen was just under 1 million. That was pretty good sample. And when we did spectroscopy, 2 of these high Q modes, which are around 2 million, responded to some spin. And if we plot them on this diagram, you see and we assumed that the origin of B versus frequency of this spin is 0. The G factor was almost 2. And if you look at these transitions, usually when you interact with a spin, the losses will create some degradation of transmission. But we saw no extra losses added by the spins. So that tells us there's an ensemble of spins which are quite narrow line width. And from the Q, the 2 million Q and the line width here, we can get an idea of what the line width of the spin is. So only 2 high Q modes were sensitive enough to see these shifts. The RF field has to be in the right direction of the modes. We could put an upper bound on the spin transition line width of 7 kilohertz, which is extremely narrow. We don't know what this species is, but it should be less than 7 kilohertz. Usually you get on the order of a megahertz. We also could do a rough calculation on the concentration, and it turns out it must be below 10 to the 11 centimeters cubed, which is extremely small concentration too. Usually for residual impurities, you would have 10 to the 15 or something like that. And the reason you can see it is because of the narrow line width increases the magnetic susceptibility to make the experiment sensitive. So assuming the spin passes through the origin, the G was around 2. So this gave us motivation to maybe look at seeing if we could put spin ensembles in silicon. We also saw a power dependence. As we decreased to the order of 1 photon, the Q actually went below 1 million. And that was how the line shape changed. And you can just take the Q off that. So we had large quality factors and a reasonable Q at single photon energy. So what we decided to do, what we've done now, we haven't sort of published this yet, but we will soon, is that we chopped this, after measuring it, we lent this off these Russians, and then after we'd done the measurements, included them as authors, they then proceeded to sell it to us. So they sold it to us. They could have sold it to us in the first place. So then we cut this into 4 cylinders, so we could use these as resonators and measure the modes and understand if we can get the same result as we got in the rod. Okay. So you can see there's a nice polished surface on the top, and it's not so polished on the sides. And now we can predict the modes in a much better way. We've got a regular shape. We can predict the modes. We know what we're looking at. And so these cylinders are about 14.9 millimeters high and about 15 millimeters in diameter. They've got a hole drilled through the middle so we can support it, and we can see these modes. This shows you a whispering gallery mode with 7 variations around, and we modeled that in COMSOL. So we measured the Q factors of these, and they were pretty bad. They weren't as good as we saw in the rod. But nevertheless, we could well identify the modes. We know the mode structures, where in that other experiment we were only guessing what the modes were. We could from the modeling we could work out the permittivity. We used these 4 modes to determine the permittivity. We come up with a permittivity determination which is only determined by the dimensions. The precision of this is much better, but we cannot measure the dimensions as well. And of course you don't have a perfect cylinder, so when you take that into account, this is what we measure the permittivity of silicon to be at low temperatures. So what do? We've got this bad result, so we're collaborating with a group in Melbourne University, Dave Jamison's group at Melbourne University. One of my postdocs went to work with him and we're working together. So we take this and we do Raman spectroscopy on the surfaces, and we can see that when we have a look at different places, there's a scatter which says there's strain. So we put this through a process which they know, which gets rid of the strain in the silicon, and eventually, after annealing and these acid baths, we look and we see that the surface is now not strained anymore. We found that the polishes on the surface, the polished surfaces were fine. They didn't have excess strain. It was the cylindrical sides that were the problem. So here's an example of these things going in the furnace, red hot. You could put that on your barbecue, I guess. And after this, machining, the Qs were an order of 10,000, but the Qs got restored after the treatment. So I can show you after the treatment. Now we're closing in on 10 to the 6 again. These are much smaller, so it's harder to get larger Qs at lower frequencies. And some of these mode families were surprisingly lower compared to others. But nevertheless, we're now approaching 10 to the 6 again instead of being down here. So that restored the Q values, and that was a worthwhile process. And in the meantime, we could determine quite well the permittivity of the silicon. So we thought we'd do ESR measurements to see if we could see that spin again, but we don't have quite 2 million, and I'm not sure what the filling factors are. Probably similar because we've got Whispering-Gallery modes. We put it in an aluminium cavity, and we can see that transition from superconducting to normal. Once it's normal, the field then penetrates, and we do ESR. We've done that many times. Aluminium can be better than copper for losses at low temperature, even in its normal state. So we couldn't see the spins that we saw before, but we only saw it in 2 modes, and it was very low concentration. And here's an example of this, one of the Whispering-Gallery modes. We should have seen something around here, but we don't see any form of interaction. Okay. So implanting spins, we want to implant spins in the samples. Our collaborators in Melbourne do this a lot. They implant spins in their wafers. So phosphorus stove silicon wafers. We had a look at those we have a collaborator in our building that has terahertz capability, and you can look at the transmission through them at terahertz. And you can compare the doped to the undoped. There's a lot more loss. So we might be dreaming if we want to dope silicon and try and keep a high Q. There's obviously going to be a threshold there where it's a semiconductor. Nevertheless, we've implanted one of the Whispering-Gallery resonators with bismuth. The implantation was performed in Australia. At ANU, where the Melbourne guys go and do the implantation. It was implanted through the rounded sides and the flat surface. After implantation, went through the same cleaning process as we did to restore, and we annealed it to get rid of the damage. And now these resonators are under investigation, but our preliminary measurements, we haven't been able to see. We're trying to understand some excess losses in these systems at the moment, but this has only just started. Okay, and so that's work in progress. The next topic, I'm changing topics here because I'm talking about the things I've done recently, is I think this was a very interesting experiment which we published in New Journal of Physics, where we put gadolinium in, where we had a YbO4 crystal at 20 millikelvin with this ion in there. And as was mentioned in the previous talk, it's got a spin 7. So large spin system with 7 on 2. And the interesting thing about this spin as a paramagnetic impurity in a crystal is that the ground and first excited state are separated by a 7-photon transition. And therefore, that's a huge amount of photons. It exhibits non-equilibrium thermodynamic properties. And we may manipulate the population using the coupling between energy levels. So I'm going to just show these results where the first method involves a non-adiabatic passage through an avoided level crossing controlled with a magnetic field and a Landau-Zener transition. And the other one is based on cavity pumping to the higher energy state. It's a cavity-assisted process. And we see extremely long lifetimes, and that's because there's a large number of photons required for the transitions. So this is what the system looks like, the spin system of GD3+. and minus 7 on 2 plays the role of the ground state, and 7 on 2 is the next excited state until we get up to magnetic fields and we start crossing transitions. And so if we have 0 magnetic field, there's basically 1, 2, 3, 4 energy levels. And at 20 millikelvin at B equals 0, all the spins will condense into this state, and it will be degenerate plus and 7 on 2 states. So if we have no magnetic field, these should be 50-50. As at 20 millikelvin, nearly everything's in the ground state. So as we increase B, usually in a normal system, the spin relaxes to the ground state when the change in spin number is 1. But here it's 7, so we get some very different things happening. And this had me confounded in the lab for a long time before we worked it out. So here's an example of the crystal we have in a cavity, and we excite the different modes in there. So here's the interesting thing. We had this Whispering-Gowrie mode, and we hit this spin transition, which is 7 on 2 to 5 on 2. And this is a frequency of 7.4 gigahertz, and this one here is 9.4 gigahertz, another mode. And here we show the minus 7.5 on to minus 5 on 2 transition, which it crosses at this value of magnetic field. Okay, so we do this experiment, we ramp up the magnetic field, we see these 2 transitions, and then we ramp down the magnetic field. This transition's increased. The coupling's increased from 2.6 megahertz to 3.7 megahertz. And we get here, and this one doesn't exist. And so we looked at that, and we had no idea what was going on. You go up, you see some transitions, we go down. This one's increased, and this one's gone. Okay, so it turns out that here we have, if we have experimental couplings, you can see they're rough. These 2 modes we've got 50-50 in plus 7 on 2 and minus 7 on 2, and they sort of get trapped because they can't go down to the ground state because they need 7 photons, so that we get trapped with a 50-50 population until we reach this level crossing, and then that's when something changes, and when you go back, all the spins are in the excited state. There's no more spins here in this, and they're all up here in the minus 7 on 2. Oh, sorry, they're all up here, yeah. So how does that work? So usually, as we're going up in magnetic field, you would have 100% in this degenerate state, and because this is 7 photons, this will be split into 50-50, and this process will not occur. So they stay as 50-50. Then we get to this Landau-Zener transition, where the 5 on 2 and this is 5 on 2, 7 on 2 to 5 on 2. We have got these results through the Whispering-Gowrie mode interactions, and this is the 7 on 2 to 3 on 2. And when we get to this point around here, we get this avoided level crossing of the spins, of these spin states. It allows a 1 photon process. So after this 1 photon process, all this allows us to get into equilibrium, and all our spins go into the ground state here. Another interesting physical process we saw in this experiment was, here's an example of this transition that we measured on the way up. If we just put our system here for a long value of time, this transition disappeared. Okay, and so what was happening is this, what with cavity-driven thermalization, where there was this very long time constant associated with this process. It's a bit complicated, but you can see that your levels end up dumping everything back down into here, into the ground state. And you can, and here we measured these. There was an initial time constant. This depends on power. So the amount of power you got in your system, the more photons you have, and the more quickly driven the process is. So initially, this would be take a long time, and then there'll be a quicker process. And this was basically proportional to power, this time constant. So as we got lower in power, we got time constants of the order of 1,000 seconds to 10 to the 4 seconds in these processes. Anyway, I just thought I would like to show that recent results, which have took us a long time to understand. I'm not sure if they're very useful for anything, they're just interesting. Okay. I've got a few minutes left, so that's the latest work we've been doing on spins. I also want to briefly talk about some results we've got with phonons. We're coupling a reentrant cavity to a Bohr resonator, and this hasn't been published yet, but it will be soon. And if we take in two tones, we've shown we can excite the phonons with microwaves in this system. What this shows is the amplitude of excitation of the phonon with respect to offset of a pump and I'll show here a pump and probe. So if we have a microwave resonance, if we pump at that resonance, which is this reentrant cavity, and we offset the probe by the acoustic frequency, we create the phonons in this Bohr resonator to oscillate, sort of like a maser, but it's more like a CPT maser, phonon maser. What we call it we're all arguing about. That's why we haven't published it yet. But anyway, we can see bright signal coming out here, which is, and some results here. Before we put a large probe and pump power, we see a dip, which is just the experiments at millikelvin. It's just absorbing noise. Then as we ramp up the power, we excite the phonon. Every one of these points is the phonon excitation. So it's a different measurement. These are just a lot of measurements. And this looks like a nonlinear process because once we get out of the noise level, the bandwidth of this nonlinear process is increasing. As is typical in a nonlinear process, when you put in more power, the extent away from resonance that it occurs is increased. Okay, one last thing I'll mention is we also built these, I just thought it was nice to mention, we built these 3D printed superconducting microwave cavities. So if we can build 3D printed cavities, we can have a lot of, we can be very flexible in what we do. Yeah, it was done by Selective Laser Melting. I'll just go through this quick because I've spent my time. We basically use aluminium powder, which has a lot of impurities in it, but once annealed, you get rid of a lot of it. It made a bit of publicity, but it was the first printed superconducting cavity, and now we're investigating niobium. These are aluminium. You can see the cavities. They look a bit rough. They're as printed, but after annealing, microwave hole probes are drilled. We get some nice results. And so I haven't actually showing it superconducting up here. Now we're looking at niobium, and we're using reentrant cavities because we can't print very large pieces of niobium, but we can print a niobium post. And we've now just done some measurements. We can see that it goes superconducting in a copper cavity, but our precision's not very good. So now we've put it in an aluminium cavity and we'll be able to characterize that. And that's where I will end my talk, with just sort of a mismatch of latest research. Thanks.